All right, so this is about heat, and I want to explain what heat is. As Richard Feynman explained, heat is molecules jiggling. Everybody can see the sun here? It's all working, I hope. Yeah, all right. Most of our heat comes in the form of energy from the sun, but how does it travel? At the sun's core, two hydrogen atoms fuse into a helium atom, creating a huge amount of energy from E equals mc squared. And that's essentially plasma, gamma rays, and high energy photons. And once a photon is generated at the core of the sun, it takes on average 150,000 years to make its way out of the core to what's called the emission height, to the surface of the sun, where it's 5,700 degrees Kelvin, and start its 8-minute journey to Earth. It travels through space as light waves. What temperature are those light waves? What is the temperature of space? Light waves coming out of the sun are mostly high energy shortwave radiation. So is space near the sun hot? Is space near Pluto much colder? What is the temperature of space? Space has no temperature. It's undefined because there are no atoms jiggling. There's no atoms jiggling, there's no temperature. Space has about 1 molecule of hydrogen per cubic meter on average. So if photons hit that hydrogen atom, it'll gain some energy and speed up and go some direction. And that means its temperature just got higher, but the surrounding space has no defined temperature. So if light hits something larger, it warms up the bright side, while the dark side stays very cold. So you can have a difference in temperature of 500 degrees Celsius from one side to the other. It makes no sense to talk about the average temperature of anything in space, and that includes a planet. On Earth, we have shortwave solar radiation coming in. As it starts to interact with the atmosphere, some of it is reflected back to space, and the rest heats up the molecules it encounters. Eventually, all that incoming energy hits something. Whatever it hits, it causes that thing to warm, the same way that sunlight warms an apple. Now, any object at any temperature is constantly radiating infrared radiation, long-wave photons, at the wavelength that corresponds with the temperature. So you are radiating long-wave photons right now, billions of them. When struck by sunlight, the apple molecules jiggle more, and then they radiate out long-wave radiation. This is also called thermal radiation. And these are photons. They travel at the speed of light. There's no such thing as heat waves. They're light waves. And when the incoming photon hits the surface, it generates about 20 low-energy long-wave photons radiating back out. So that's kind of how you get a sense of the difference in energy. It's about 20 to 1. When you feel the warmth of a fire, that's the long wave radiation going at the speed of light, hitting the atoms of your hand, or probably interacting with a bunch of greenhouse gas molecules in the air, interacting, but then they get to your hand and they hit your hand and cause your hand molecules to speed up. And then more long wave photons radiate away from you. And anything light hits will re-radiate long wave radiation back out, except a black hole, of course. So these long-wave photons are called infrared radiation. If you have used thermal imaging glasses, you can see warm things far away because it's coming at you at the speed of light. You can't feel them, but you can see the heat because it's radiating out. When sunlight hits land, it warms it up, and that land radiates. The land does not store heat. Any heat the land gains, it gives up overnight. The atmosphere is always roughly at equilibrium. It transports heat but doesn't really store it. Despite what people tell each other in Davos, CO2 is not trapping heat and heat is not building up in our atmosphere. I explain the greenhouse effect in a separate module. Oceans cover 71% of the Earth, and they contain 99.93% of the thermal energy from the bottom of the ocean to the top of the atmosphere. The oceans have an average temperature of about 5 degrees Celsius, although we don't know because we can't measure the whole ocean very well. But it's super cold because the oceans are so deep. But oceans store a tremendous amount of energy in the form of heat. Did you know that the Earth's ocean contain about 4 times more heat than the atmosphere of Venus, which at the surface is hot enough to melt lead? That's because of the specific heat content of water, and I want to explain how that works. So, and this is one of the good images for the class to remember, and people have mentioned it already. This is the difference between temperature and heat, okay? Put a pot of water in your oven and turn the temperature to 99 degrees Celsius and let it sit for a few hours. And so everything in the oven is 99 degrees Celsius. You can put a thermometer in there and it'll read 99 degrees. The water is 99 degrees. The metal, the air, everything in the oven is at 99 degrees, okay, Celsius, which is the speed of the molecules and the atoms. But where's the heat? Put your hand in the oven. It's hot. It's 99 degrees, but you can stand it. Now, put your hand in the water. You better not do that because the water will burn your hand. 99.9% of the heat in this oven is in the water, not in the air. It takes 100 times more heat to heat the water than it does to heat the air. It takes 100 times longer to heat the water than it does to heat the air. So the water is the only thing storing heat besides the metal. So the oceans store about 1,000 times more heat than the atmosphere, and the land stores no heat from the sun. All thermal effects are in this ratio. So when you talk about heat, you're talking about 99% of it being in the oceans. This crude model helps us understand that the Earth's climate is driven mostly by the sun, with the oceans absorbing energy, storing heat, and releasing it later. But the Earth has temperature gradients. Temperature is the speed of atoms. Heat is the number of atoms at that speed. So heat requires a large number of atoms. Heat is the sum of the speeds of many atoms or molecules. So if you double the number of atoms, but you keep the speed the same, you double the amount of heat, even though the temperature hasn't changed. It's a big difference between temperature and heat. So which has more heat? Desert air at 50 degrees versus humid tropical air at 30 degrees. The desert is hotter, but the jungle has more heat. Can you see that?
Yeah.
It's the difference between temperature and heat. So let's look at the temperature gradient. And this is for the Earth. And this is 100 million years ago during the Cretaceous. The Earth is on its side here because this is the equator. And then this is the North Pole here, and this is the South Pole. And we've looked at many of these during our previous classes. During the age of dinosaurs, the gradient was fairly flat. It was hot. There were no real cold places. There were mild seasons and not very many storms because storms are driven by heat differentials. So this was a very hot, and also this was 100 million years ago, the end of the Cretaceous. This is very steamy, very wet, sort of saturated atmosphere that would have been very, very cloudy as well. And this is the temperature gradient for hothouse Earth 34 million years ago. And this is a little flatter, and it's about as hot as the Earth has ever been. You wouldn't be able to see it like this because it would have been covered with clouds. And this was just before, remember our previous look at the history of Earth. This is just a million years before the Middle East closed 33 million years ago and deflected the equatorial flow of water south toward Cape Town, where it escaped then over the South Pole, and Antarctica began to freeze. And in very short order, Antarctica froze up, say in a million years or so. And then this gradient started to change. And 14 million years ago, the Isthmus of Panama closed. That's another module we've studied. And that started the northward flow of water that created the northern ice caps. And since 14 million years ago, we've generally had ice at both poles, and we've been in an ice age since then. So this is snowball Earth, which was probably about 750 million years ago, and again at 440 million years ago, probably for different reasons. And the Earth was farther from the sun. Temperature at the equator here is below zero, so there really was ice at the equator as far as we know. And the poles probably had lakes of liquid CO2. There might have been CO2 rain and hail. Remember, the steeper the temperature gradient, the more heat has to move from the equator to the poles to escape, because the sun is always sending the same amount of energy every day. So it's got to move heat from the equator to the poles to get out. So here's a summary of all these temperature gradients. This is latitudinal temperature gradient or meridional temperature gradient. And here's where we are right now. This is our current temperature gradient, this thicker blue line. And you can tell we're not that far from severe icehouse. We are in an ice age because of the Earth's ability to move heat out through the poles. And without that, it's more stuck and it builds up. And so right now we have kind of a ventilating situation, and the shape of the continents and the currents in the ocean determine the shape of this line. So this is just my first quick, unit on heat and temperature. And then it's just meant to be like a little, teaser, because we use this concept in class all the time, don't we? The difference between heat and temperature all the time. Heat is speed, temperature is speed, and heat is mass, thermal mass. Okay.